Well, I've got obviously a question on this wind turbines. So, Philippe, do you plan to take into account the rotation of the turbine?
The rotation of the turbine. It's interesting that you mentioned that. So the rotation of the turbine is will be important because that's an effect that we'll have to deal with in the sense that the turbine are you don't have the choice. You know, you have wind, and they are actually generating some noise through this rotation. So it's something that with high wind, as you can see on this slide, you will have to face. What is interesting, more than the rotation of the wind turbine on the turbine itself, it is the rotation of the structure. We will deploy some rotation sensors at the bottom of a few wind turbines. So what happens is that because of the rotation of the turbine, because of the wave motion and everything, the turbine itself moves like that, and the rotation sensors that we will deploy will tell us about this physics. You know, it's something that is quite uneasy to measure, rotation sensors. And so on top of classical seismic sensors that measure normal motion or classical motion, XYZ, we will have rotation sensors to see about the torsional vibration associated to either the turbine itself or the seismic wave field.
So actually you mentioned torsion. So do you expect to have on top of flexural and compressional resonances some torsional resonances?
We expect to see that, yes. And we would like to see whether this could be connected to metamaterial physics to understand that. Yeah.
Okay. And in terms of this wind turbine, so they are attached, they are clamped to the bedrock. How are they connected to the soil?
So I'm not a specialist of wind turbines, but in our team, people are much more expert on this. So yes, I mean the idea is to have a wind turbine that is attached as much as possible to the sediments, you know, such that it will not fall, you know, because the force on the wind turbine is tremendously big. So yes, I mean, so it's done different ways depending on the soil structure. I mean, they can sometimes dig very deep. Sometimes, finally, I mean, the soil structure is such that they can anchor the wind turbine without having to dig to dig. So I'm not in the two wind turbines field that we will investigate. I'm not fully sure of how the turbines are anchored, so I cannot tell you.
Okay, very interesting. So yeah, please, you can ask a question. Yeah.
Okay, thank you, Philippe, for this very nice presentation. So just to stay on this problem of wind turbine, so I suppose that you would like to study the dual functionality of the wind turbine. Is it the case? So with respect to the airborne structuration for the sound propagation in air, so this is for the noise, and also for the seismic protection. Is it the duality of the functionality you would like to study, or just elastic waves? Or...
So very interesting question. We will mostly focus on seismic wave because that's really our expertise. Okay. So the seismic sensors, we expect them to measure the propagation of surface waves and just to see how the scattering associated to all those resonators will transform the wave field when we are inside, when we put all our seismic sensors or geophones inside the wind turbine field. So that's the first order effect, I would say, that we would like to see. And what we would like to see is that the decorrelation of the wave field, especially, is much faster inside than outside of the collection of wind turbines. Now, what you say about the air scattering associated to is also very interesting. But here wavelengths are much smaller because we will have wavelengths on the order of maybe 10 to 20 meters, depending on the acoustic frequency. And so here we will be more in a kind of we are not subwavelengths, you know, between those resonators. We could have effects, but something that is a bit more far away from the metamaterial physics that we try to demonstrate. But interesting, yes. So we'll have also some LIDAR measurements on the different wind turbines, just to measure their deformation, and potentially to measure a part of turbulent wave field in the air. But I'm not sure that this will be very connected to seismic wave field.
So do we have any more questions? I'm sure we do.
Hi, I'm Fernando. I don't know if you can hear me. I had few connection problems.
We can, Fernando.
Okay,
Please.
okay. I had some connection problems before. So very interesting seminar. Thank you very much. This adds to the ongoing research on significantly adds on the ongoing research on seismic metamaterials. I'm working on a similar but at the same time different topic. So I'm working on the seismic materials at the at a smaller scale, at the scale of single structural elements. So instead of the scale of the building or the scale of the site, I'm working on the metamaterials that can be used at the seismic isolators with in the below a column or a beam of a building, or maybe in between the foundation and the columns of a building. So I would like to know if you have any ideas of hints about directions for smaller scale seismic metamaterials.
So smaller scale. I mean, do you see my the screen again? Can you see the,
yes,
the slide?
yes, no,
So a lot of work has been also done with the idea of really seismic protection. At the moment, I must confess that we are just with the tree experiment and so with the wind turbine experiment, we are just more playing with physics, you know, wave physics, and without really the idea of protection. We are just having fun with nice physics at the seismic scale, I would say. But people are actually making a lot of progress. And here you can see the work from Palermo et al. Published in scientific reports, where they indeed think of seismic protection with some buried surface resonators. And depending on the soil velocity, the protection is much dependent. I mean, the seismic protection could be effective with different mass, you know, because again, you know, the role of the mass versus the role of the speed is tremendously important. So this work is still, I mean, it's not the work that I'm pursuing, but it's very interesting, and you can have some very different type of resonators. This is another one that you can think about and look at the size of this mass with some strings everywhere, and the potential effect of the wave, the incident wave from the left, when you reach this kind of seismic barrier. So definitely, it's a whole field in itself that is developed by colleagues in Italy and other places.
I have also another idea. I have also another idea that I would like to discuss with you in the future. So another idea that I had is that you're looking at the site. You're looking at the site of the building site or the foundation of a building as a metamaterial. But it would also be possible to look at the building the building itself as a metamaterial, because you can have, for example, you can think of a periodic structure of a building that attenuates seismic waves when they move through the height of the building, and also you can have kind of the unit cell can be the interstory of a building can be the unit cell, so you can think of a metamaterial at the building as a metamaterial. Or we are also experimenting some metamaterials as a seismic isolator. So I think it's nice to explore different directions of different uses of metamaterials concepts for the seismic protection. Your direction is the original one, which is very fascinating, and I know this field has been initiated by Sebastien and other colleagues in France and somewhere else. And I think that there are other directions that can be explored, looking at the building as a metamaterial, and also maybe smaller components as a metamaterial.
I agree. I mean, that's I would say that's the ultimate goal, to see how buildings could behave as coupled resonators. And as I told you, I mean, as I described at the beginning of my talk, that the ingredients are there, in the sense that we have some very tall buildings in cities like that that are at the subwavelength scale, and we can measure at the same time with geophysics equipment the wavefield with a spatial configuration of seismic sensors, 10,000, 20,000 seismic sensors deployed in a city. So we know how to do it, and we even have some data. And so definitely investigating a city to see how it behaves as a metamaterial is a very strong interest, and this probably will be done in the next few years, I guess. The simulation that I showed here is a simulation that was done by Andrea Colombi, where he just mimic Quito downtown here on the left, so Quito in Peru, just to see with SpecFEM how the buildings behaves together to scatter the wavefield. So the difficulty is to be sure in this physics what part is due to simple scattering to the part that is due to the resonance effect of coupled resonators, because you'll have scattering if you have buildings and seismic wave. Obviously, I mean, it has been observed everywhere. Now, is it enough to lead to metamaterial physics where you expect to have really some band gaps or strong attenuation in a given frequency band and some energy that is trapped into the building and slowly released into the ground, such that you have a slowdown of the velocities inside the city. So scattering, obviously, and then potential some cancellation of wave, but is it really metamaterial physics? Okay, I mean, I'd like to see some data in order to be convinced.
Okay. Thank you. Thank you.
Very nice. Do we have any more questions? Yeah, please do, Professor Zhang.
Yeah. So thank you very much for your nice talk. And I'm very, very interested in your research subject. At the beginning, you have mentioned usually seismic waves have very, very low frequencies. And the most here reported works in literature, they are still dealing with quite high frequencies, maybe 13 or 40 or 15, hertz. Do you know, or are you familiar with any really works? Yeah? a very, very low frequency between 1 and 5 hertz, you know, have been done.
No,
Yeah?
I mean,
Yeah.
you mean experimental work with
Yeah,
with
experimental.
experimental work.
Yeah.
At the moment, I would say no,
Okay.
because it's difficult to excite wave at such low frequency. I mean, you need a vibrator track, and even vibrator tracks have difficulty to reach 5 hertz. You know, I mean, they work well at 8 to 10 hertz. You know, above, of course, but below 5 hertz is complicated, and that's where we would like to actually see waves. You know, so you have then only to release, I mean, you have to deal with seismic waves. You know, through earthquakes, but they are not very frequent. Also, so the combination of a controlled source below 5 hertz, a grid of sensors that is sufficiently good to see wave propagate, and a collection of very tall resonators as buildings, so far has not been really observed, the combination of these three ingredients. But again, I'm completely sure that it will be done in the next 10 years, and maybe in the next 5 years, somewhere in the world.
Yeah, thanks. This is also my feeling, and I think until now here, and no really works, you know, have been done, and for frequencies below 5 or below 10 here, it's really tough for experiments and even for simulation. Thanks. Yeah.
Wonderful. Do we have any more questions?
I have one.
Yes, please do.
In fact, you talked about tall pillars. What is the kind of criteria to say it's a tall pillar? Is there a ratio between the height and the radius, or the height and the diameter?
Interesting. So, okay, to be sure that I understand your question is about if I have a tall resonator, like a beam or rod attached to either, you know, that could be a tree or attached to a plate with, if it's at the lab scale, what should be the ratio between the length and the diameter in order to see the effect? Okay. So, very interestingly, in the past, meaning the last 20 years, there has been many experiments with what we call metasurface. So at the plate, at the lab scale, metasurface are just plates on which you can put some very small rods that could be 2 centimeters high and tall, you know, that you can organize, order, disorder, and people have sent waves and they have demonstrated some Bragg effects and so on and so forth. Okay, so the fact that you have here in our case, we use very long resonators because with very long resonators, we were able to separate the resonance effect. It was easy to interpret the resonance because with very long resonators, either you have flexural motion or you have compressional resonances, and it's easy to sort. When you have a rod that is only, let's say, 4 centimeters in height and 2 centimeters in diameter, it's going to be complex, you know, because you have torsional mode, you have flexural mode coupled with vertical, and you will be able to do the experiment. It's going to work, you know, Bragg scattering will occur in this particular case, but the resonance effect really associated with very long and very tall resonators is more difficult to observe, you know. So we used very long resonators in order to separate the physics, you know, and to be able to understand. Now what matters, remember, is in order to really see a good effect, is the relative mass of the bar with respect to the local mass of the plate. So that is very important. And second, it is it is a coupling, meaning that if you have a plate made of duraluminum, and if you use a rod that is also made of duraluminum, the coupling is perfect. You know, so wave is going to propagate, everything is good. But if you have a plate, and now if you put on top of that a bar made of plastic with a very poor coupling with the duraluminum, the physics will be very different, you know, meaning that you will have difficulty to put energy into your bar because it's made of plastic, and the mismatch between the plate wave and the bar will be very different. So it's a combination of the relative mass and the good coupling that makes the physics that we observe.
Okay, so there is a ratio. So it's like we should take 1,000 for every 1 in radius. So we should have 1,000 in length, something like that, the ratio.
But I mean, then it depends a little bit on your parameters. You know, you can clearly see for any kind of length and size of a bar in width, you know, how are scaled the compressional versus the flexural resonances, and you want to separate them easily. You know, so there are some equations. It's easy to define. You know, mathematically.
Okay.
You know, what you just want to do is to be able to separate the resonances as no ambiguity on what you look at. And that,
okay.
I mean, yeah.
Thank you so much.
Okay.
Excellent. Do we have any more questions? Emile, for instance?
Thank you. Thank you for the very interesting talk. I was thinking about the strategies that we can go about, and so far was wave steering and maybe dispersion control or something like that through the band gap openings. And now I would like to point out several other strategies, and that will be more in line with what Fernando was saying. These tall buildings to be seen as antennas where you just somehow couple through the atmosphere and release these waves in the atmosphere. So they so for them to act as antenna, and then we have also sort of vibrational capacitors, the metamaterials, which can absorb a lot of vibration while not increasing the amplitude. So that will be sort of metamaterials with a very high density of states, exactly where the frequency of the incoming wave happens, and that will also be a solution, because then the metamaterial will have the capacity to absorb a lot of this vibration without increasing the amplitude. And then the second observation and question about the forest experiment was that we learn about the effect of the roots, but we never learn about the effect of the leaves, which couple very strongly with the atmosphere, and they create this antenna effect. Who knows? I mean, for sure, there was a lot of dissipation precisely due to the leaves. So it will be very interesting to repeat the experiment once in the summer and once in the winter. Maybe that will be too much, because also the soil will be very different. If you could comment on any of these.
Yeah, very interesting. Nice comments. So maybe the second question first. But so we dealt with pine trees. So even in the winter,
okay.
for human, unfortunately, you know,
There were pine trees.
Yeah, maritime pine trees. So, but the effect of the leaves is definitely something that we have no way to evaluate. You know, it's very complicated. The dissipation that we can have through that, even the dissipation with just the roots is already very complicated. Actually, it really depends on the way the roots are connected to each other, and so on and so forth. And so it's very. I mean, it's interesting. I mean, we do not have also the numerical tools to be able to really model trees, and see the difference between a tree without branches and a tree with branches in order to see how dissipation modify the dispersion curve and so on and so forth. I mean,
for example, in the diagram where you showed a resonant mode of the trunk, were you able to assess the width of the resonance?
Yes, I mean the width of the resonance we could, and the Q factor was relatively the one that is expected for trees, But
which is, do you remember what is the Q factor like?
It's on the order of 20, something like that,
Oh, that's a fairly big Q factor.
Yeah, definitely. You can see that the resonances are quite peaky for the flexural resonances, and the flexural resonances couple a bit less with the seismic wave, with the Rayleigh waves. So that's why the Q factor is a bit stronger. The Q factor was less, maybe just less than 10 for the compressional resonance, and
so I should make a comparison. It's almost the same in the same ballpark with the plasmons.
Yeah. I mean, the physics is not the same, but it's not trivial from just this Q factor to determine what is the effect of the coupling to the soil and how the waves, coupled with the tree. With respect to the attenuation associated to branches and foliage and so on and so forth, and that is, and as you say, I mean, the way to do so would be to do an experiment with, let's say, poplar trees that are very tall and very massive in the winter and in the summer, because here at least you do not have the foliage. That would be fun to do. But it's interesting to think about that. This, numerical simulation to reproduce that is tough to do, I would say, because it requires some numerical tools that are extremely, with a meshing that is extremely dense and not easy. Going back to your first question, that makes me think that was probably what you had in mind, some energy harvesting, through metamaterial physics. It's also, I mean, it's very interesting. That is very interesting. At the moment, I'm not completely clear in my head about, the possibility to do some real energy harvesting through those resonance coupled resonators. But there must be something to do here in this field, how, the advantage is that there is a trap of intensity of the waves, and if the wave do not penetrate into the plate, the waves are inside the trees or the beams anyway, and there is maybe here a way to collect this intensity through the capacity, adjusting the good frequency. So I think it's very interesting that that's physics. People begin to explore the use of metamaterial. I mean, they've been doing so for a few years already as a way to harvest some energy. Pincheng is working on that, and other people with some black holes, metamaterial, whatever. So yes, I'm not very familiar with this physics, but I think that it's very interesting.
Thank you. What I was thinking, if these bars that you are using, they were just straight bars, if you will do some patterning on, just simple patterning, that might open some some effective ways, in fact, to go to study such effects.
Yeah, sure. Yeah, interesting. Yeah.
Speaking of which, in the same spirit, tree trunks, they are orthotropic media. It's not isotropic, because they have this, this kind of concentric circles. And I wonder what is the effect of this orthotropy. It might have an effect, because really, so far, all the people involved in this kind of, tree, roads, models, they have always assumed that it was homogeneous isotropic.
Sure. Yeah.
Which is, what is the effect? Perhaps it's minor, perhaps it's...
Yeah, no, you're right. It's definitely not an isotropic medium. And again, you know, how to really evaluate this effect on top of all the others, not trivial, but interesting.
I'm getting back to a question, you know, related to this. So, okay, there is a foliage. So this has been mentioned by Emile, but something you mentioned already are the tree roots. And your kind of graphic seems to show that the trees are connected via their roots. It's some kind of network. And you mentioned that you simulate this by some kind of effective layer, perhaps?
Or effective, how do you say, effective elasticity, I would say, you know, I mean, effective Young modulus through because I mean, the ground is the same everywhere, but you have some roots, and the roots definitely for pine trees, they are not very tall in the ground, but they are very spatially extended. So it's not surprising. I mean, it will not be surprising that the trees are also connected through their roots, not only through the ground, but through their roots. Maybe that's also what we're observing. You know, we don't know. Maybe it's just a connection with all the roots of the trees that are actually then activated by seismic waves. You know, that makes this coupling between the trees. And so at this stage, what we can only see is that at a frequency that is a relatively low frequency, so far away from the resonance of the trees, we have a higher velocity in the forest than in the field that is next to the forest. And the order is not big, but it's something like 10%. You know. So the Young modulus of the forest, of the soil inside the forest is a bit different. It could be also the additive mass of the trees, you know, that weight, you know, this weight, you know, in a kind of effective medium could just maybe explain a velocity that is a bit stronger, maybe. I do not know too much about that.
Another effect might be the anisotropy, because since the roots are really elongated, this adds an effective anisotropic layer, perhaps, you know.
Very interesting.
So perhaps this would, you know, give some kind of preference to certain types of, you know, longitudinal motions, or, you know, there should be a prevalence of, due to the effective anisotropy, because you can really see in your diagrams, I mean, this kind of preferential, it's a effect that you can.
I mean, you are more wise than what you think. I mean, we have 15 days of continuous ambient noise, and when we deal only with ambient noise and we measure through the grid of sensors, we measure the beam pattern, we clearly see that we have anisotropy. So we see at all frequencies that it is an anisotropic medium, meaning that there is a preferential direction that is actually at 45 degrees. If we here we have a x and y at 45 degrees, we have waves that goes faster than in any other direction. I mean, so it's a kind of ellipse like that when we, instead of a circle, I would say. And so far, I do not know how to explain that. It's an observation. It works very well. It's very nice. I could show you the results, but I have no explanation for this anisotropy. And maybe what you say is a start of an explanation. I'd like to. I don't understand why it's in this direction actually, instead of this direction or and so on and so forth. But
yeah, 45 degrees is quite intriguing.
Yeah. And it's something that we clearly observe every day, and you know, and it's also something that we have difficulty to actually demonstrate with active sources, meaning that the active source, I mean, the anisotropy, I mean, the wave, the circular wave propagation is, I mean, we do not have enough data quality to really be able to say that at 45 degrees we have velocity that is higher than other direction. But with ambient noise, because we accumulate over 2 weeks, the final resolution of the beam pattern is extremely good, and we can actually prove that we have this anisotropy observation. Now we have no interpretation, and interesting to discuss.
Yeah, together with Agnès and Kim, I think there's an effective, you know, there are models that might
that would be extremely
figure out, you know, I have a last question. It's again, I mean, this question, you know, it's maybe it's a bit dummy, but when the wave enters the forest, of course, it enters some kind of diffusive medium. And so sometimes, you know, for light, people model the diffusion of light with this kind of fixed law. You know, it's can you envision to actually replace the full Navier model by a much simplified model where you replace, you know, the governing equation by some kind of diffusion equation inside the forest? Would this, I mean, because when I see, you know, this SpecFN numerics, it makes me think of some kind of diffusive medium, no?
Interesting. I don't think that is really. I mean, it is more resonance than scattering, and because it's more resonance effect than the scattering effect, I would be careful with using diffusion, where actually, to me, diffusion relates to multiple scattering and intensity, propagation of intensity, or, you know, this kind of average. And when you have a very strong resonance effect, can you really use the diffusion equation to mimic or to explain or to interpret the propagation of intensity, or, you know, whatever? That I don't know. And but here I see that John is with us, John Page. So obviously John has the answer to this question.
Yeah, it would be really great to have the input of John Page, if John would oblige.
So John, it's a question for you.
All right.
Okay. Okay. No. So yeah, I'll be cautious with using the diffusion equation to do that in the regime where we have the strongest effect. So in the regime where the trees really behave together. Okay.
What was the velocity of the waves?
Do you want to comment on that issue
Yeah.
of diffusion and when it's relevant, perhaps?
Please do, John.
I mean, in one of the systems we have just studied, the one we see Anderson localization in as well, in a certain frequency range, the description is more like the type binding model description. One starts with the resonances of individual spheres, in this case, that are strongly coupled together. And it's that gives rise to passbands, because the propagation is through the system of resonators, as opposed to having two media, one in which resonators are coupled to when you're studying the propagation, and the other medium in some sense. So I think maybe they're different, but certainly in our case, there is strong scattering. The spheres are disorderly configured, they're coupled together, and the modes of propagation are coupled resonances, just as in the tight binding model for electron transport. And so scattering is very strong, the coupling is, you know, weak. The overlap of the wave functions in the tight binding model for electrons is weak. And it makes sense to talk about scattering, but it's not the same picture as a plane wave coming in and scattering off a bunch of discrete scatterers, which is the usual picture we have in mind when we talk about diffusion approximation. But in this other case, coupled resonators in the medium of propagation, it can also be used quite effectively. For, of course, describing the coda, not the coherent part of the wave. And one has to be careful to separate the two in this sort of discussion.
Okay, thank you, John.
A reasonable answer.
Yeah, that's a good point. When you put sensors on the trees, were you able to look at some correlation functions between the readings?
Yes, we have some spatial correlation between neighboring trees that are associated to the flexural resonances. So it was especially strong at flexural resonances, so around a few hertz. And we are trying to interpret that at the moment. So it was this is very interesting to look at. That's still a work in progress at the moment.
Because I think if you have that data, then you can build a model in this regime which John was mentioning. So you just look at the trees, and through these correlations, in fact, you can build a tie binding model for the trees, just for the trees.
Yeah, definitely. I mean, that's what we have in mind. Unfortunately, we do not have that many trees that are equipped with, you see here, all those are the trees that were equipped with some velocimeters in order to, with our 3-component velocimeters, so that can also measure the horizontal motion. And that's where, with the horizontal motion, that we can actually observe this spatial correlation. But it's a bit, I mean, okay. We would like to have more spatial extension of this investigation.
I'll guess the correlations will just, everything will be decorrelated beyond, say, second nearest neighbor.
Except at the resonance, the flexural resonance of the trees, where it expands much on much longer scale. So that's very
it expands.
Where you can have then the trees that seem to be coupled, but it's not the neighbor, not its neighbor, but 2 or 3, 4, 5 trees.
Okay. So that's very interesting, because it's almost like the difference between solid and liquid, where you do have long range correlation. So, and in a liquid, you'll just see.
So, but we don't have that many of those kind of observations, and so okay, we are looking at that at the moment.
Yeah, it's not an easy, because you have to control the phase and the amplitude. So, but if you can do that, that's very valuable data.
Yeah, exactly.
Quite interesting. And I was wondering if such data can be collected just by letting the wind go through the forest, sort of having.
So we had some windy periods during the 15 days, and so we and because we have meteorological data, we can check, what happens. And yes, of course, the flexural motion of the trees is the horizontal motion of the seismic sensors at the bottom is much stronger when wind excites the trees, the whole forest.
Yeah.
So that's what and so it's a combination of this effect and also some spatial correlation that could potentially lead to.
So the wind can serve as a source. So use it as a source. The correlation should be independent of what source you use, something. So just to use the.
But you need an excitation, in order to observe some spatial correlation. So what was interesting is to see that when the wind is strong, the horizontal correlation of seismic centers that are attached to trees expands on distances that is much longer than the distance between two neighboring trees. Okay, I mean, is that enough to conclude? I'm not sure, but that's at least an interesting observation.
So I wanted to ask, what was the wave, the speed of the waves you observed, for example?
So here you see, I mean, the Rayleigh waves, they travel at around 325 meter per second, you know, inside the forest. So that is meter per second for surface waves. So it's pretty low. The soil is kind of very mold.
Yeah, well, you'll say it's low. To me, it looked very high.
Okay.
So 300 meters per second.
Yeah.
It's due to the fact that it's a soft soil.
Subsoil.
Sorry, soil.
But can you have higher speeds? For example, if you, in rocky places.
Yeah, way faster, 3,000.
Way faster,
yeah, but for example, if you go outside LA where it's sandy, sort of, then it will be much smaller.
It could also be smaller. Yeah, we could have in very wet and soft areas surface waves at the top that is on the order of 100 to 200 meters per second. Yeah. 1/3 of that. Yes, definitely.
So you can outrun them with a sport car,
yes,
like in the movies.
We can imagine Tom Cruise on his motorbike with Mission Impossible and the Rayleigh wave, you know.
It's going faster.
Okay.
Yes. Okay.
Do we have any more questions from the participants? I think we had really a great question and answer session with almost 1 hour of interaction, and it's yeah, it's great. I would like to thank everyone for their input today, and thank you so much, Philippe, for this wonderful talk.
Thank you very much. Thank you for the invitation.
And bye bye everyone, and stay safe.
Bye.
Bye bye. Thank you.
Bye. Thanks, Philippe.
Bye.
Wonderful talk.
Indeed.